Welcome to this explainer. I am absolutely thrilled to have you here today because we're going to completely demystify the complex and, yeah, sometimes intimidating world of coordination chemistry. We're not just going to sit here and memorize textbook facts. Instead, we're building our understanding from the ground up using a trusty tool belt approach. By the end of this, you are going to have the exact structural tools you need to decode these incredible chemical compounds with total confidence. Let's get into it. Here's a quick look at our roadmap. We'll be hitting double salt versus complex, the structure of coordination compounds, and ligands, types, and features. After that, we'll dive into oxidation, coordination, and EAN. Check out synergic bonding, and finally, nail down those IUPAC naming rules.
All right, kicking things off with Section 1, double salt versus complex.
Imagine you mix up some aqueous salts, you heat them up until the water evaporates, and boom, you form a brand new solid addition compound. Now, normally, when you toss a salt back into water, it just completely breaks apart into all its individual ions, right? But I want you to think about this for a second. What happens when a salt stubbornly refuses to break apart? What happens when it maintains this sort of secret identity, even when it's fully submerged?
Well, that stubbornness actually highlights the core difference between our two main types of addition compounds. On one side, we've got double salts, like potash alum. You throw these into water, and they scatter completely. Every single ion goes its separate way, and will give you a positive test in an aqueous solution. But on the flip side, we have complex salts. When a complex salt like K4FeCN6 goes into the water, it only partially dissociates. It's fiercely protecting an inner fortress. The constituent elements inside that fortress absolutely refuse to separate and act independently.
So, what exactly is going on inside there? That brings us to Section 2, Structure of Coordination Compound.
To really understand this inner fortress, we need to meet the two main characters running the show. First up, think of the central metal ion, or the CMI, as a really powerful but resource-deficient boss. It's a Lewis acid, meaning it has vacant orbitals and desperately needs electrons. Surrounding this boss are the ligands. Think of them as the electron-rich donors, or the employees. Their primary job is to literally donate their lone pairs of electrons to the boss, which forms a super strong covalent coordinate bond.
Now, the really crucial point here is how we visually write this all out. Take a look at our anchor example, K4FeCN6. See that square bracket? That acts as an exclusive VIP room, which we officially call the coordination sphere. Inside that VIP room, you have the iron boss and the cyanide employees completely locked together. And waiting patiently outside the brackets are the potassium ions. We call these counter ions, or the ionization sphere, because they will easily dissolve in water, unlike the VIPs safely locked inside the bracket.
Moving right along to Section 3, ligands, types, and features. Let's officially meet these employees.
We measure the capability of our ligands using a handy term called density. Density is basically the capacity of our employees. It tells us exactly how many coordinate bonds one single ligand unit can form simultaneously. Some employees are monodentate. They can only handle one task at a time, providing just one bond. Cyanide is a great example of this. Then you have bidentate ligands, like oxalate, which can form two bonds at once. And then you have the absolute superstars like EDTA. EDTA is a hexadentate ligand that can juggle an incredible 6 bonds simultaneously. It literally wraps completely around the metal boss all on its own.
But you definitely want to watch out for a tricky category known as ambidentate ligands. These are employees with two totally distinct skills, meaning they have more than one potential donor atom. Take our friend cyanide again. It has both carbon and nitrogen. But here's the catch. They can only ever use one skill at a time. Why? Well, if one single cyanide molecule tried to bond with both its carbon and nitrogen simultaneously, it would form this tiny, incredibly tight 3-member ring with the metal. That creates impossible structural angle strain. It just wouldn't hold. So they smartly stick to using just one donor at a time.
All right, time to bust out the calculators for Section 4, Oxidation, Coordination, and EAN.
There are two specific numbers you absolutely must keep straight here. The coordination number is super simple. You are just physically counting the total number of coordinate sigma bonds surrounding the metal inside that VIP room. Easy. But the oxidation number, that is an imaginary concept. It's the net charge the central metal would have if you completely stripped away all the ligands and all the counter ions along with their associated charges.
And once you have that oxidation number, you unlock a really powerful formula, the effective atomic number, or EAN. The formula is Z, which is the atomic number of the metal, minus its oxidation number, plus the total number of electrons donated by all the ligands. This final number is crucial because it shows us exactly how stable the metal boss has become after hoarding all those donated electrons.
Let's watch how cleanly this calculates out for K4FeCN6. Step 1. Iron's atomic number is 26. Step 2. The oxidation number is +2. We know this because the 4 positive potassiums outside mean the bracket is -4 overall. Since we have 6 -1 cyanides inside, the iron absolutely has to be +2 to balance things out. So 26 minus 2 gives us 24. Step 3. We add the electrons from the ligands. 6 cyanides provide 2 electrons each, which gives us 12. Finally, 24 plus 12 brings us perfectly to 36. And no way, look at that. 36 is the exact atomic number of the highly stable noble gas krypton.
Now let's shift gears a bit for Section 5, Synergetic Bonding.
Welcome to the wild world of metal carbonyls. In a normal complex, the ligand donates to the metal. It's strictly a one-way street. But when carbon monoxide acts as a ligand, the dynamic totally flips, and the metal boss actually gives back to the employees. If the central metal has a high electron density, it pushes those electrons back into the ligand. This creates a really fascinating two-way street of electron flow that we call synergic bonding.
The physical, real-world consequence of this back donation is honestly just incredible. First, the carbon donates a lone pair to the metal, forming your standard sigma bond. But then, the metal takes its own packed electron orbitals and actually back donates them into the empty anti-bonding pi orbital of the carbon monoxide. Now, because electrons are entering an anti-bonding orbital, the bond between the carbon and oxygen actually weakens. So the metal-carbon bond gets stronger, but the carbon-oxygen bond order decreases, causing the CO bond length to literally stretch out. It is a brilliant microscopic balancing act.
Let's bring it all together with Section 6 IUPAC naming rules. To talk about these compounds universally, the IUPAC rules give us a strict 4-step sequence. First, you always name the cation, the positive part, before the anion. Second, when you're naming the inside of the coordination sphere, list your ligands alphabetically, using numeric prefixes like di, tri, or hexa to show how many there are. Third, write the central metal's name. But remember, if the coordination bracket itself is negatively charged, you've got to add the suffix -ate, so iron becomes ferrate. Finally, drop the metal's oxidation state right at the end, in Roman numerals and parentheses. Apply this to K4FeCN6, and it elegantly translates into potassium hexacyanoferrate 2.
We have unpacked some truly hidden chemical fortresses today, from denticity and oxidation states to the incredibly cool two-way street of synergic bonding. But true mastery is all about putting it into practice. So I'm leaving you with a challenge. Can you calculate the EAN and the official IUPAC name for the unique neutral complex NiCO4? Think about how these exact synergic bonds and structures allow scientists to engineer the chemical catalysts that literally power our modern world. Dive into that calculation, keep building your tool belt, and never stop questioning the atomic structures all around you.